Thank you. Hello, everyone. All right, so I did something crazy, and I wrote most of my presentation in live view, so it's going to be fun. We'll see how well it goes. Oh, look at that. Well, that's pretty crazy. Oh, anyway, so hello, everyone. So I'm Zack, and I am here to talk a little bit about purely functional data structures and Elixir. So before we get started, I kind of want to get a feel for who in this audience is familiar with the book Purely Functional Data Structures by Chris Okazaki. Just a show of hands. Looks like about 4 or 5 of us. So that's great. So the cool thing about this talk, I hope, is that I'm bringing some of the work that he did and trying to talk about how does that work in the context of Elixir. So a lot of this talk is going to be based off that book. So if you're familiar with it, that's great. If you're not familiar with it, like 100% recommend going to Amazon and checking it out. There's also a white paper that you can check out for free on the internet. So what I'm showing here is I've got a little bit of a red-black tree updating itself. So my goal here is not to conjure up bad memories of your data science class or data structures class from CS 101 or 201 or whatever you had back in the day, but just to get a feel for where everybody's at in kind of terms of the data structure background that you've had. So who all here is from a CS background? All right, cool. So it actually looks like the majority of us are not from the CS background. So very cool. I am also not from a CS background myself. So who all here has taken a data structures course in their life at all? Okay, so it's quite a few of you, it looks like, have taken a data structures course. And so how many of you here have ever implemented a red-black tree for fun? There was 2 people that raised their hand for that, so good stuff. And so for the 2 of you that did you implement it by chance in C++ or Java? No? Oh, 1 person did. Which language, sir? C. Oh, that's beautiful, beautiful. All right, so when we're talking a little bit about data structures, kind of in our basic course, we learn about things like queues and stacks and a bunch of other things. And red-black trees are kind of cool just because there's like colors in them and stuff, and like they look cool. So I really had trouble kind of wrapping my head around like what a red-black tree was and like how it would update. So I made a live view thing that would show me what was happening when it updated. But for some of us who are coming from kind of an object-oriented background, maybe you implemented these things in Java or C++ or some kind of object-oriented language. And in those languages, we rely mostly on mutating the state of an object, right? So for example, with this tree here, so let's say we have like 3 elements in the tree, and we want to add another element. So what happens in an object-oriented context? Well, we just take our object, our red-black tree, we change it, we mutate it, and now we have 4 things in the tree. But what happens to that old tree with 3 things? Is that still available to us in the object-oriented context? It is not, right? In a functional context, so what we're doing is essentially what looks like a copy, right? So we're making a copy of the thing with 3 elements, and then we're adding another one. But what that means is we actually have an old version of that data structure, right? We still have that available to us if we want to use it. And then we have this new structure with the extra element added, okay? So a lot of what I want to talk about is like, what does that mean for us? Like if we're copying things and kind of have all of these different versions of a single data structure, living kind of this expanse through our application, what does that mean for us? What are some of the implications? What are some of the dangers of that? And how can we address those? How can we work with those in Elixir? So the cool thing is Elixir kind of gives a lot of this for free. So by purely functional data structures, let's kind of set up just a little bit of terminology before we start. So what do we mean by purely functional data structure? So I'm going to give just a very kind of hand-wavy type of definition here. So I think probably all of us, so is everyone using Elixir here? Whether in production or just for fun? All right, cool. So it looks like a lot of us are using Elixir. So I assume we're all familiar with this, right? Our data is immutable in Elixir, right? Would everyone agree with that? Okay. So this is immutable versus in like object-oriented languages, we have mutable data, right? So the other thing is our data structures are persistent. So this is an interesting point that I want to talk about in my talk. So the persistent side of the data structures are actually provided to us by Erlang, or the beam, essentially. And the opposite of this is ephemeral. So what that means is, in the example of the red-black tree, right? If we implement that in C or we implement that in Java, we have a tree with 3 elements, and then we add an element. We have a tree with 4 elements now. That means that old tree with only 3 elements that no longer exists, those things are ephemeral. Persistent data structure means you have different versions of the same underlying data that live throughout your application, right? It doesn't die when you update. Okay, so just a quick note on persistence. So I know we have this kind of like definition, I think, in our head of whenever we're talking about software and persistence, we generally think about what? Database, right? So in this context, for the context of this talk, we're not talking about persistence in the database. We're talking about it as a way for us to have different versions of the same data structure alive in our application. And essentially what this means for us is that instead of updating values by mutating stuff, we actually have new data structures based off the old data structures that can live and coexist in the same space. All right, so that's all well and good. So for some of us who came from kind of an object-oriented background to Elixir. All right, cool. It looks like almost everyone who raised their hand about doing Elixir came from an object-oriented background. So when you started working with Elixir, was this your first functional language? Show of hands. All right, so it's a little bit fewer. So it looks like some people had done functional languages before. So I just want to ask a quick question, kind of gauge how you feel about this. So when you came to Elixir and you realized that you had immutable data, did you think this when you started? Yes. So there's a few people shaking their heads, and there's a few people nodding. So it's like a 50-50, that's great. So the truth is, right, copying data can be inefficient, right? So for example, like, what if you want to have like immutable data in JavaScript, and you're just like, I'm just going to like copy all my objects everywhere, and that's how I'm going to get immutability. That's probably not very good. So in functional languages, essentially what we're doing here is we use a technique called sharing. So sharing is what allows us to get immutable data structures with copying pretty much as minimal as we can, keeping the copying to a minimum. All right. So sharing is caring, yay! So sharing it basically, to give you an overview of how this works, there's essentially 3 steps to sharing, right? So the first thing is you're going to copy only the affected nodes in a data structure. So you can think about this like in the context of Elixir. If you think about a list, let's say you have a list with 3 elements, right? So, and then you want to maybe add another element on. Okay, so when you have the first element, that points to a tail with these 2 elements right in the back. The second element has a tail with 1 element, the very last element, right? And now you want to add another thing at the very end. So in that case, you would have to copy all of those nodes, right? You have to copy the first, the second, the third, and the fourth. But if you want to add something onto the head of that list, you're just putting a new thing on at the very front, and essentially what you can do is just point to the old list, right? And then that gives you your new list. So you're only copying nodes that are affected. So the second thing that you're going to do is when you make a copy, you're going to make all of your changes in the copy, right? If you want to update an element or something, you're only going to make the changes in the copy. So this means that that old data structure is still there and available to you. All right, and then the third step is you're going to share all nodes that are unaffected between the two. So I just want to look at a couple of examples of what this looks like. We'll start with the basic example of lists. So let's say we have two lists here. We have artists, Leo, Raffi, and Mikey, my favorite Renaissance artist, of course. And then we have three kinds of tortoises. There's a snapping, a box, and a soft shell. So I want to look at what happens if we want to concat these two lists together. What does that look like in the way that the data is managed in memory? So we have our two lists here, right? So Leo's the head of artist, right? And it points to a tail where the tail is another list and the head is Raffi. And then Raffi points to a tail where another list and that other list's head is Mikey, right? So the same thing for tortoises here. So now what happens if we want to concat those two things together? So what we're going to do is we're going to copy from artists first, right? So is Leo going to point, when we concat these two things together, is Leo going to point to the same tail that it was pointing before? Is the tail for Leo going to be exactly the same as what it is here? So no, right? So it's mostly the same, but there's a problem here because when we copy over to Mikey, now Mikey is going to be pointing to a different tail, right? So what we have to do is we have to copy all of those nodes all the way up to Mikey, and then we can just copy by pointing to the first element in our tortoises list. All right? So that's kind of one example of how that works. So let's take a look at a quick second example. So imagine we have this update function on lists. And so all this is going to do is you're going to say, I want to update the element 2 in a list to be another thing, right? You're just going to change one element in the list. And so the way that would work is, so does anyone speak Spanglish here? No? Any Japanese speakers? No? Okay, so I spent some time in Japan, and there's a thing there called Nihonglish, which is English and Japanese kind of mixed together. And I am very fluent in it, if you would like to speak Nihonglish with me later. So in my example here, what I'm trying to do is make a list of Nihonglish numbers. All right, so I'm just going to throw in the Japanese word for 3 in place of the English word for 3, right? So that's the second element, or third element, if you're zero-based. I want to throw that in. I'm going to replace 3 with that thing that's like 3 lines. That's how you do 3, because of 3 lines in Japanese. So our result here will be 1, 2, 3, 4, and 5, right? So what does that look like when we're updating? All right, so the first element, is that going to be pointing again? Is that going to be pointing to the same tail, the exact same tail? No, right? So Nihonglish, we start with 1. We're going to have to copy that, right? Then we're going to have to copy 2. And then we're making a change in the next element, right? We're going to change that to be 3. And then from there, we have the same tail, right? So we can just point to the 4, which is the next element in that list. All right. So what happens when we have like something that's a little bit more complex in terms of the way that the data is laid out than a list, right? So lists are pretty straightforward. But what if we have something like a tree structure? So how does sharing work in the context of a tree? So is everyone familiar with a binary search tree? All right, looks like a few of us. So essentially, this is just a tree structure, and you can just imagine things are ordered in a certain way so that you can see the root there, D. Everything on the left of D is less than D, right? And then everything on the right is greater than D, okay? So what happens when if we want to update this thing? So, for example, if we have an insert function available on this, and we want to insert E into the tree, what exactly would that look like? So what do we have to copy here to give us our new tree? So the first thing we're going to do is, can we just keep the same tree? Is it going to be the same tree? No, right? So we're going to have to start at the very top, the root. So we're going to take a D, and we have to copy that. All right, so we're inserting E, right? So when we insert E, it's either going to go on the left or the right, so it's either greater than or less than D. So is E less than D? No, right? So that means that we can just use the same left side of that tree as we used before, right? So this new node can just point to the old left side of that tree, right? On the other hand, it is greater than D, so we're going to have to copy the next node there as G, right? And so now we're at G, and we need to insert E still. So is E greater than G? No, right? So you all are very good at letter ordering. So here we can point directly to the old node, right node of G, and we don't have to do any new copying, right? So on the other hand, it is less than G, so we're going to have to copy the next node there, F. And then obviously the next thing that we have to do is just place E. So what we've done here is we've copied only 4 nodes in a 7-element tree. So that saved us quite a bit of copying, right? It saved us quite a bit of work. And all of this is really done behind the scenes for us in Elixir, so we don't really have to think about this much. But it does present some interesting problems. So especially in Elixir, the thing that I want to keep everyone to focus on for the rest of the talk kind of is, in Elixir, there's a kind of an evaluation strategy for all different languages, right? So there's strict languages and there's lazy languages. Elixir falls more on the strict side over here. So does anyone know any lazy evaluated languages? Haskell, exactly, right? So there's a few other languages that would fall under the lazy. Yes, very good. So I think Closure. Is OCaml lazy evaluated? Is it strict? So there's a few languages that fall under the lazy evaluation strategy. So strict, this is our default evaluation strategy in Elixir. So what does that mean for us? Doesn't really mean all that much to us if we're just programming your regular old straightforward synchronous kind of program. But it does have some implications, right? So this is kind of a very contrived example, of course, but adding is, I think, pretty easy. You all did a very good job at ordering letters, so I assume that you'll be good also at adding 2 numbers together. So we have this strict module here that I made, and so basically at the very bottom there we have an add function, right? So we can add 2 things, A and B, and then in the function itself it's going to print out to the console adding 2 things together, and it's going to add A and B, and then that's going to give you your result, right? So the interesting thing here is, what if we call add with function 1 at the top and function 2 at the bottom? So what would that do? So this is going to print out, if you look at what it does, function 1 is going to print out running function 1, and it's just going to return the number 1. And function 2 is going to say running function 2, and it's going to return the number 2. So we're going to add 2 and 1 together eventually to get 3. But if you look at what's happening here is when we run those, we get the output from function 1 and function 2 first, right? So those are getting evaluated first before the add function gets evaluated, and then it returns 3. So the insight here is that in Elixir, our parameters are getting evaluated first. So big deal, right? Like, what does that mean? So what if those parameters that we're passing in are really expensive functions? Is that good or bad? Like, very bad, right? Like, what if your function 1, instead of just returning 1, what if it was like calculating pi to like 5 gajillion digits, and then function 2 is doing something else? And then also, if you want to think about this, right, what happens if you don't need one of those things? So say, for example, you have a condition inside of the add function where you don't actually need the result of function 1, you only need the result of function 2. Well, Elixir is going to evaluate function 1 no matter what when it gets passed in, right? So is there a way to get around this in Elixir? Yeah, I heard a few yeses, and the answer is yes, that is right. So how can we make Elixir a little bit lazier. So one approach is we can just throw things into functions, right? We can just return anonymous functions. So this is one way to make it a little bit lazier. So if we change that last module up a little bit to return anonymous functions instead of returning just the numbers themselves, right? Then we can call add with 2 functions and then evaluate those inside of there. So this means that when we call add with function 1 and function 2 here, what do you think the output from those things is going to be? Undefined? Perfect, right. So it's going to call the outer function for first, and then it's going to evaluate those 2 functions passed in as parameters inside of the body. So that's going to change the order of our output, right? So it's going to say adding 2 things together, running function 1, running function 2, and then it's going to return you a result. All right. So that's all very well and good. And so that evaluation strategy is, in fact, has a name. It's called call by name. So that's lazy evaluation, where you're basically just passing functions around that are going to get evaluated when they're needed. So like it says here, this lets us defer evaluation of arguments. But there's actually another evaluation strategy called call by need. And I think Haskell is well known for this. So what that is it's a memoized version of this. So let's say you have some expensive function and you need the result from it. So you force it to be evaluated. So once you force it to be evaluated, the result of that function is cached, right? Basically, it's memoized. So subsequent calls to the same function with the same inputs is going to return in constant time, right? It's going to return immediately because it's just pulling it from a cache. All right, so what does memoization do for us? So going back to what we were talking about earlier with persistence and sharing and functional data structures, memoization is key for working with persistent data structures where you might have some complex long-running function, and maybe you can call it like a few times against the same data structure, right? The same version of a data structure. So when that happens, if you're using strict evaluation, that means that it's going to take a lot of time each time you call those functions, right? It's going to take, however long it takes for it to evaluate. So something like this would be kind of bad, right? If somebody knew how to invoke a function in your system that took a lot of time, they could clog up your system using something like this, right? So on the other hand, if we have memoization here, this would only be evaluated the first time you call that function, right? So this call here with memoization would take a lot of time, right? It would have to evaluate, figure out what the result is, and store that in a cache. The subsequent calls to that are going to return immediately, right? Just looking things up in a cache and then returning to those 2 immediately. All right. So the question here is, can we replicate this in Elixir? Can we replicate these semantics? And what would that look like? So obviously, it's a strict language by default, right? So we're going to need to set up some things on our end to make this work. So we're going to need a few things. The first construct that we're going to need really is called, I'm calling it a suspension. And a suspension is just a way to defer the evaluation of a function call, okay? So that's the first thing. And the way that we can represent this, so you can represent it as a struct or a map that's just a container that has a single function that you want to run later. The second thing that we're going to need is a way to memoize the results from that, right? So we have to figure out what the result of that function call is, and then we're going to have to store it in a cache and be able to retrieve it later. And so the last thing is, if we have these suspension wrappers kind of around a function, we're going to need a way to tell them to evaluate their function call. So we need a way to force the evaluation of those things. All right, so what we have then is we can have a little module that looks like this. So there's a suspension module, and it's a struct here that has only one key, fun, for a function. And then maybe the API looks something like this. So maybe you have a create function that takes a module function and your arguments, and then it wraps it in a suspension struct where you pass in this function here. And we're going to assume that we have a thing called Memoize that's going to do the memoizing and caching for us. All right, so the second thing here is we just have a force, and a force is going to evaluate a function, if there's a function there, or if it's not a suspension, it's just going to return the value, right? It's just a pass-through. All right. So one downside to this is that would get kind of messy, right, if you're trying to use that in your application, because then if you have something like an add function, you would need to look for suspensions being passed in, and then you would also need to look for just regular primitive values being passed in. And that's not very fun, I think. All right. So instead, what you can do is you can make a little bit of a macro, and we're going to call it the def lazy macro. And what that will do is it will let you pass in either primitive values, right? You could pass in numbers like 1 or 2 to this function, or you could pass in suspensions containing those things. And then inside of it, the macro is going to take care of forcing those suspensions if it needs to, and it will also just handle regular primitive values as well. So you could do something like this. You can pass in add. Maybe you have a suspension that's holding the number 1 and a suspension holding the number 2. And then you could do add with primitives where you just pass in 2 primitive values, 1 and 2. And then if you force both of those, you're going to get the same result, right? So that's essentially what the def lazy macro is doing for us. All right, so what I did to kind of show you like what this looks like and how it feels to use is I made a lazy stream module, which basically just mimics the stream module in Elixir. So it's a watered down version of that. We've got append, take, drop, reverse. And then the other thing here is I made a couple functions to create lists from those things, from those streams, and also a way to make a stream from a list. So I want to take a quick look at what this looks like here. So I made kind of set this up a little bit earlier. So I made a stream that has the numbers 1 to 3,000. And then I made a suspension where we're going to reverse that. And so this is actually going to take, when we force it, evaluation of this, it's going to take a long time. So I'm going to do that right now because that seems like a good idea. That's not what I want. All right, and I'm just going to hang out and drink my water. Oh, that's really slow. Good performance here. It'll finish eventually. Oh, there it is. Look at that. Yay! Excuse my excitement. All right, so now that we've evaluated it, right? So now, let's do a suspension force of the reverse suspension again. So it's going to return immediately now, right? Because the results are cached. All right, so that's basically what the def lazy macro is going to do for us here. So the next thing I want to talk about is with streams like this, when you have lazy evaluation, your functions now get a little bit more complicated. So there's 2 things, 2 different characteristics of your functions. In this example particularly, there's 2 different kinds of behavior. One is called incremental. The other one's called monolithic. And the lazy stream module that I was just showing you has a couple of functions that are incremental and a couple of functions that are monolithic. So what does that mean? So if we look at something like the append and the take functions, those are incremental. And what that means is they only do enough work to produce one cell of your data structure. So if we actually look at what that looks like, here is append, right? So you can see here, in the bottom case of this, right here, our tail is another call to append, right? But since append is defined with def lazy, what does that mean? So def lazy is just going to return you a suspension automatically. It's not going to evaluate anything. It's not going to force evaluation of any of your suspensions. So basically what you're doing here is you're going to get a new cell. So cons is just basically a container for a cell. And then the tail there is going to be a suspension. So that's not going to get evaluated at all. All right. On the other hand, we have monolithic calls to something like drop. And what this means is that we're going to call in here to another recursive function, drop underscore. And once we start evaluating this, once we force the suspension that gets returned from def lazy, it's going to keep calling drop recursively until it's computed all it needs to give you its result. So that's going to do a little bit more work there. Okay. All right, so the last thing I want to take a look at is kind of maybe conjured up some bad memories from data science or data structures classes, but hopefully not. So just from a show of hands here, who's familiar with, is everyone kind of comfortable with worst case running time, like analyzing data for data structures for worst case running time? Yeah. Okay, so this is, just to give everyone kind of just a quick brief background on these. So when you're analyzing a data structure for worst case running time, basically you're essentially looking at what would be, in the worst case scenario, how long would a function call or some kind of operation on a data structure take. So in the case of lists in Elixir, if you're searching for something in a list, the worst thing that can happen is it has to search all the way through the list, right? Maybe you have like 1 million elements, and if the thing is at the very end, it's going to have to go through all 1 million of those things to find the element that you were searching for. So worst case is just concerned only with specific operations, right? How long would it take to call a function, to evaluate a function in the worst case? So in this case here, I want to bring up a little bit about amortized analysis. So who's familiar with amortized analysis here? All right, so there's only about 2 or 3, maybe 4 people it looked like from that. So amortized is kind of just an extension to worst case. It's a little bit different from worst case because instead of focusing on how long a single function call or a single operation would take to evaluate, it's thinking about how long would it take to evaluate a sequence of operations, right? So any arbitrary sequence of operations that you can call on a data structure. So when you're thinking about designing data structures in Elixir or in any language really, this is all kind of valid to you. What this does over worst case analysis is you don't have to worry about analyzing individual running times for any operation. But instead, like I mentioned before, you're thinking about a sequence of operations. And basically, how this helps is that it will allow us to think about kind of broader solutions to get efficient operations on data structures. And it kind of opens up our design space so we can think a little more broadly about what data structures and what operations on those data structures will work for us. All right. So there's been kind of study and research into amortized data structures for a long time. So the Purely Functional Data Structures book that I mentioned at the beginning of the talk, that was written in the mid-90s, or the white paper at least was written in the mid-90s. And before the paper was written, traditional amortization was done only with the context of strict evaluation, right? So in traditional time, or traditional amortized analysis, we're thinking only about what happens for strictly evaluated languages. So that applies to us in Elixir. So what we're doing here is we're just defining the amortized cost for each operation. And then you need to prove that the amortized cost, so whatever you define it as, you have to prove that the amortized cost for any sequence of operations is an upper bound on the actual cost of that sequence. And so this allows for some operations to actually exceed their amortized costs. And so the important thing here is this gives us the idea of accumulated savings, right? So as you're building up your data structures, you are essentially creating savings for yourself over time so that you can call more expensive operations on those things later. Okay. And there is a thing called the banker's method. And I just wanted to show this because it was my only GIF. And it was that was the best banker GIF I could find. All right. So we're running a little bit low on time here. But essentially what I want you to think about here is in the context of strict evaluation, you're building up savings. But in the context of lazy evaluation, what's happening is you're creating a lot of work as you're building up your data structures that you're deferring to a later time. And so in that context, you're doing something more like creating debt for yourself, right? You have to pay those things off later. Because at some point along the life cycle of your application, you're probably going to want the result of some of those deferred evaluations, right? So the key to kind of reconciling strict evaluation and lazy evaluation is to think about how do you need to structure your data such that you can have an efficient call, efficient way to evaluate some of your suspensions there. So there's a little bit more I wanted to get to, but I'm going to leave it for maybe hallway chat later on. So I made a thing here that calculates your amortized costs of a queue, which is pretty sweet because I did this in live view. And that's all I'm going to say about that. All right. And then I just want to finish up with a few resources. So if you're interested, like I mentioned at the beginning, a lot of this talk is based on this book here, Purely Functional Data Structures by Chris Okazaki. There's also a white paper that you can find at this URL here. And then the third thing here, there's another paper that was written before Purely Functional Data Structures about analyzing data structures in a strictly evaluated functional context. So that's a lot of words. This is pretty interesting because a lot of the techniques created in this paper apply to Elixir. And the last couple of things here, I have a few of the data structures that he talks about in Purely Functional Data Structures implemented in Elixir at this GitHub URL here, if you're interested in looking at that. And I also have these slides available for anyone to look at, and they're all in live view, so that's pretty cool. I hope it works. My live view function worked. Cool. And then just to wrap up, so thank you very much. And then, so just a shameless plug for myself and my company. So I work at Gaslight, which is a consultancy in Cincinnati, and we do a lot of work with Elixir. I think we have about 3 Elixir projects going on right now. And if you're interested in talking to us about that or any of the things related to that, you can visit Team Gaslight or just come up and talk to me afterward. But again, thank you all very much.